In this video, we're going to look at how we can write the elements of the motion group of the cube as permutations. And the very first thing that we need to do is we need to look at a cube. So let's look at a cube. And I'm going to use some dotted lines to get the back sides of the faces shown. And I want you to imagine rolling this cube around and having it land in exactly the same space that it's currently occupying. Well, one thing that we're doing is we're permuting the corners of the cube around, and the corners are called vertices. And so one way that we can think about writing the elements of the rigid motion group for the cube is to label the vertices in some kind of a fashion. And every rigid motion is then going to be a particular permutation of the vertices. Now, what this means is that we can think about the motion group, so the whole set of rigid motions, will then be a subgroup of S8, the full permutation group that is acting on the set 1, 2, 3, and so on up to 8. Now, clearly, the motion group is not all of S8 because the motion group has order 24, and the order of S8 is 8 factorial. So it's a very small subgroup, but it's one way that we can get our hands on looking at the motion group. But that's not the only way that we can do it. So I also want to look at a slightly different idea. Another thing that I can think about is that the cube has faces. It's got a front face, it's got a back face, it's got a right face, and it's got a left face. And of course, it's got a top and a bottom. And every rigid motion is also going to permute. So every rigid motion is also going to permute the faces around, so we can think about each rigid motion as being a permutation of the faces. And in other words, any rigid motion is a permutation of the set right, left, top, bottom, and front and back. And there are 6 elements in this set, and let's think about that. There are 6 elements in this set, and what that means is that we can think about each of the rigid motions as being some element in S6 when S6 is acting on that set. Now, to simplify the notation just a little bit, I want to realize that right, top, front, and left all start with different letters, but bottom and back we have to abbreviate more clearly. I will use BAK for back and BOT for bottom because my A's and O's often look alike. Well, what we've now got are 2 different important ideas. We've got the idea that we can look at the motion group and we can embed it inside of S8 by thinking about the rigid motions as permutations of the vertices. We can also think about the motion group as being a subgroup of S6 by thinking about the rigid motions as permutations of the faces. To make this idea more concrete, we need to actually look at a couple of examples and write particular rigid motions as permutations of the vertices and permutations of the faces. So let's go on to looking at that idea. So in this particular slide, what we've got is we have a permutation that sends the standard picture of the cube, that was not what I wanted to do, that sends the standard picture of the cube over here, and I'm calling this permutation by the name alpha. And it turns out that alpha is pretty easy to see. Alpha is the permutation that spins the cube around a line that goes through the center of the top and the bottom, and we are going to be spinning it 90 degrees in the counterclockwise direction. And if I want to write alpha as a permutation of the vertices, all I have to do is use the same convention that we used in the dihedral group videos. Vertex 1 lands in that corner, and that is the 4 spot. And so what I want to notice is that that means I'm going to write 1 goes to 4. And 4 is over here, and that's the 3 spot. So 4 goes to 3. 3 landed over here, and that's the 2 spot. So 3 went to 2. And 2 landed back there, and that's the 1 spot. And that completes the first disjoint cycle in alpha. And so we now look at what happens to the bottom. And it's no surprise that if we start with 5, 5 lands in the 8 spot. And 8 lands in the 7 spot, so 8 goes to 7. And 7 lands in the 6 spot. And 6 lands over in the 5 spot, and that completes that particular permutation. It's no surprise that if you do alpha 4 times, alpha to the 4th is going to be the identity permutation. In other words, the order of this particular permutation is easy to see that it is of order 4 inside of S8. But what if I want to write the permutation as a permutation of the faces? So let's write the same alpha, but this time embedded inside of S6. Well, what I want to notice is I do the exact same thing. Top is fixed. Top over here is in the top spot. Bottom over here is in the bottom spot. So if I want to be very explicit, I can say top went to top and bottom went to bottom. Now, what about, let's start with front. So we wind up thinking about where the front face winds up over here on the right side of the cube. So what that says is that front goes to right. Well, where does the right face land up? Right lands up over here, and that's on the back side of the cube. So right goes to back. Well, what about the back side of the cube? Well, back lands over there, so back landed on the left side, so back winds up going to left. And left lands over here on the front side of the cube, and so that means left goes to front, and that completes our cycle. So in disjoint cycle decomposition, alpha can be thought of as front goes to right, goes to back, goes to left. And again, it's easy to see that alpha to the fourth is going to be E inside of S6. And so this is inside of S6. Well, okay, that was a really easy rigid motion. Let's make this whole idea a little bit more concrete by going into the next, by looking at a second example. Okay, here's our second example. Beta is just going to be the rigid motion that takes the standard position of the cube into this position. So let's just say beta does this. Now, it's a whole lot harder to just look at this picture and figure out what the actual rigid motion of beta is. So the first thing that I want to do is I want to simply kind of look at trying to figure out what beta is in terms of permuting the vertices around. So we'll start with 1. 1 wind up down here, which is in the 6 spot. So 1 went to 6. We're now going to look for where the 6 winds up. 6 winds up down here, that's in the 8 spot. So 6 went to 8. Now we go looking for where 8 wound up. Well, look, 8 winds up way back there on top. That's the 1 spot. So 8 went to 1, and that completes our first cycle in the disjoint cycle decomposition. Well, let's see. We have not accounted for 2, and so let's look at 2. So 2 is over here, and that's in the 7 spot. So 2 went to the 7 spot. Well, let's see. We go looking for the 7 over here. 7 is up there, and that's in the 4 spot. So 7 went to 4. And now we go looking for 4, and 4 is up there. That's the 2 spot. So that completes a cycle. So 4 went to 2. And let's see, we haven't dealt with 3, so let's find out what happens to 3. 3 is over there, and that just happens to be in the 3 spot. In other words, 3 is fixed by beta. And if we look at 5, it turns out that 5 is over here, and that's the 5th spot. And so what does that mean? Well, what that says is that beta fixes 5. Well, if we start thinking about it, we can now make some sense out of what beta is actually doing. If I think about drawing a line that connects vertices 5 and 3, what beta is doing is beta spins the cube along the diagonal joining vertices 3 and 5. That's what the actual physical motion here is. Well, okay, fine and dandy, but how does beta permute the faces of this cube? So let's see how the faces get permuted. Well, let's again do the same kind of trick. Over here, we see that top lands over here on right. So that says top went to right. We go looking for right, and we realize that right is on the front of the cube. So right went to the front. And let's see, where did front go? Front is up here on the top of the cube. So that says front went to top, and that completes that cycle. Well, let's see where bottom goes. Bottom. Bottom lands up over here. That's the left side of the cube. So what does that say? That says we want bottom to go to left. Well, now where does left go? Left, when we find it, left goes to the back side of the cube. So that says that left goes to the back side of the cube. And then what happens? Well, back, when we find back, back lands on the bottom of the cube, and that completes that cycle. So to clean this up just a bit, when we're thinking about beta being a permutation of faces, top goes to right, goes to front, bottom goes to left, goes to back. That is a permutation inside of S6. And one of the things that I want to notice is that regardless of which of these ways that I'm thinking about beta, both of these permutations are going to have order 3. If you take this permutation inside of S8 and compose it with itself 3 times, since it's made up of 2 disjoint 3 cycles, beta cubed will be equal to E. On the other hand, if I look at this permutation in S6, it's a composition of 2 3 cycles, and so beta cubed again will be equal to E. It's good to know that no matter which way we're thinking about it, the order doesn't change, because that would obviously have to be the case. And that completes this video.